My name is Mackenzie Poncel, and this is my Physics 2211 Lab 2. In this lab, we will show how the laws of physics explain the motion of a falling object. According to the momentum principle, a change in momentum means that there is a net force acting on the system. Because the velocity is changing over time, I can determine that there is a net force. This experiment uses Python to create computational models of the motion of an object. I used a motion tracking software to determine that the object is acted on by a net force and compared this to the computed values from the code. For calculations, I used the velocity update formula and the position update formula seen here on the left, and on the right this is their format in the code. I also used weight force and drag force seen here on the left, and then on the right is their format in the code. You see with the drag force, I used the drag coefficient B, which I will tell you how I determined later. This is my data for the motion tracking software. You can see as I drop the ball, I plot the center of mass in each frame as the ball is moving. Those plots then get put onto the position versus time graph seen on the right. Below that is my data point. You can see that the time starts at 0.00 seconds and goes until 0.567 seconds. This is the data that I used to experimentally determine the position of my ball as it fell. Here is my data for the computational model that is going to show the drag force. You can see in the beginning that I initialized the ball's mass, initial position, and initial velocity, which were both 0. You can see here that I initialized the B, which is the drag force coefficient. I determined that experimentally. I plugged in values for B until I got a final position for the model close to the final position of the experimental model. So you can see I used the while loop to include the fnet and iteratively determine the ball's position over time. When this program is run, you can see that the blue arrow is the drag force and the orange arrow is the weight force. As the ball is falling, you can see the position versus time graph and the velocity versus time graph of the ball as it falls as well. This is my experiment position versus model position with no drag. You can see that the red dotted line is the model position and it very much overestimates the experiment position. This must mean that there is another force acting on the ball as it is falling, which is affecting its position. Here is the falling ball versus time, which includes the model position with drag and without drag. You can see that the yellow dotted line, which is the model position that includes the drag force, more closely aligns with the experiment position. However, it doesn't quite match up completely. Though it is accounted for, the model and the experimental values do not match completely. Like I said before, this could be due to other forces interacting with the ball as it falls, such as wind. The terminal velocity of an object happens when drag force and gravitational force are equal and opposite. According to my models, the ball did not reach terminal velocity as it fell. This would have been shown as a linear function because velocity is constant. However, the models can predict when the ball would have reached terminal velocity. When a falling object reaches terminal velocity, it no longer accelerates, which means that the total net force acting on the object is 0. So, what if the ball was thrown with an initial velocity instead of being dropped from rest? The terminal velocity would still be the same. Here on the left, I show a velocity versus time graph when the ball is not given an initial velocity. The terminal velocity is negative 2.8 meters per second, and you can see that that happens right here before the 1 second mark when the velocity becomes constant because there's no acceleration. Here on the right, I show another velocity versus time graph where the ball is given an initial velocity of negative 5 meters per second. You can see that the terminal velocity is still negative 2.88 meters per second when the velocity becomes constant, and it still occurs at the 1 second mark. When an object is given an initial velocity greater than the terminal velocity, like in this case, the object falls and it decelerates until its speed matches the terminal velocity. In the other sense, when it's not given an initial velocity, it accelerates until it reaches that speed.